Welcome to RC Scientific. In this video we will give detailed insights into the drivetrain and the acceleration capabilities of an RC car. We will first derive a model of the entire drivetrain to predict acceleration. After validating the model, we will then use it to show how we can increase acceleration. But be aware, there will be a lot of mechanics and maths. Acceleration of any object depends on the amount of force acting on it and the mass of the object. It can be computed by Newton's equation. In a car with wheels and motor, acceleration also depends on the moment of inertia of the wheels. The smaller the moment of inertia, the faster is the acceleration at the same forces. And the acceleration depends on the moment of inertia of all the gears, shafts, axles, and other rotating parts of the drivetrain. Let's take a closer look into the drivetrain of a Traxxas TRX-4 chassis and determine its overall gear ratio. The gearboxes of the drivetrain between the motor and one wheel include the pinion Spur Gear, the main transmission, one differential, and one portal axis. In the following you see how the overall gear ratio of the drivetrain can be computed. Now let's take a closer look at the rotating components inside the gearboxes and connecting links. This includes the motor, the transmission gears, the drive shafts, the axle drive shafts, and the wheels. In the following slides we derive the moment of inertias of each of these components. The overall moment of inertia of the entire drivetrain can be computed as follows when knowing the gear ratios of each individual gearbox and the moment of inertias of all the rotating components. To compute the acceleration of the car, we also need to know the force acting on the car. This force is given by the force produced by the motor after taking into account the efficiency of the motor and drivetrain. The force accelerating the car depends on the motor torque, the overall gear ratio, and the distance between the ground and axle, which is a value that is a bit smaller than a wheel radius in an unloaded condition. The motor torque was experimentally determined only for the static case. This torque is called stall torque and it applies only for zero or very small rotational speeds. Attention! This test is not recommended because the motor gets really hot due to the missing cooling in that static condition. Further values needed to calculate the acceleration are the moment of inertia derived before, the dynamic rolling radius of the wheels, and the mass of the entire car. The mass has been determined by a weighting scale for the front and the rear separately. Finally, the acceleration for the first and second gear can be computed using all the values presented so far. Two conditions must be fulfilled to be able to realize these rather high acceleration values in a real setting. First, there must be enough friction between tires and ground. With friction values of the TRX-4 Defender tires determined in another project, C-Link, we can derive the maximally possible accelerations on the different grounds, or the required friction coefficient to realize the accelerations computed before. We see that for anti-slip, grass, and tar, the friction seems to be just sufficient to realize the computed accelerations, but not for stone. The second condition is that the accelerated car must not tilt backwards when accelerated. This can be analyzed by applying the equilibrium condition about the potential tilting point. For this, the location of the center of gravity of the car must be determined, especially its height and horizontal distance from the rear axle. In the following, we calculated the critical acceleration that would lead to a backward tilting. The acceleration computed before for the first and second gear are indeed a little bit higher than this critical acceleration. This leads to a backflip, also known as a wheelie effect. The maximum speed of the car can be determined on the basis of the kV value of the motor used, the applied battery voltage, and the overall gear ratio. Note that we simplified these computations by ignoring any load usually acting on the motor, drivetrain, and car. Nevertheless, the resulting speeds at first and second gear roughly correspond to the speed values known for this RC car model. Using our formula for acceleration, we see that we can maximize acceleration when first increasing the motor torque and/or overall drive efficiency, second decrease the mass of the entire car, and third decrease the moment of inertia of the wheels and other rotating parts within the drivetrain. With respect to the overall gear ratio and wheel-related parameters, it is more difficult to make clear recommendations. Here it depends which part of the denominator is more dominant, and this depends on the actual gear ratio applied. To achieve high accelerations at high gear ratios or low gears, we recommend to decrease preferably the moment of inertia of the motor, increase the wheel radius, and decrease the overall gear ratio. Gear ratio can be reduced, for example, when choosing a motor with a lower number of turns. Assuming low gear ratios, we can do the following analysis with acceleration. For reaching high accelerations at low gear ratios, which is at high gears, we recommend to decrease wheel radius and to increase overall gear ratio. Of course, we are aware that the TRX-4 is a crawler, not made for high accelerations. Nevertheless, it was a convenient model that can give us insight into the drivetrain and explain aspects of acceleration. Thanks for watching RC Scientific.